Limits are one of the important underpinnings of calculus, which are going to help us understand how we can look at functions and determine rates of change. But to begin, we need to understand what a limit is. So the limit is a number. It is the dependent value that a function approaches as the independent variable approaches some value. So what that means is we're going to consider what happens to the y value as we get really close to an x value. So for some of the functions we look at, the limits are going to be very intuitive and we should be able to guess them. But the idea is that when we get mathematically good at computing limits, we can then look at more difficult functions. The notation when we're looking for a limit looks like this. The limit as x approaches c of f of x equals L. So L is going to be our dependent value that we're approaching. And C is the independent value that we're going to be approaching on the x plane. So what we're again doing is we're considering what value of y we're approaching as we get really close to some value of x. So let's look at an example with some concrete numbers to sort of solidify this idea of what limits are and what parts of this definition are really important. So let's consider the function given in this graph. We have an increasing function that's concave up. It appears to be continuous with no holes or jumps or anything that's concerning here. So first we have to determine which limit we want to find. We have to decide which x value we want to approach. So let's start by looking at the limit as x approaches 2 of our function. So again, we have to pick the value that the independent variable is approaching, and then we want to consider what value y is approaching as we get close to 2. So the word approach in our definition is really important because we're never going to actually plug in 2. We're going to try to get really close to 2 to see what y value we're getting really close to. So here, if we pick values on either side, we can then see a little pocket where our y value has to live. So I've picked x values about halfway between the integers, right around 2. So the idea is that we want to get closer and closer to 2. So I get closer on either side, and then I look at what happens with my y values. So here, as my x values got closer to 2, my y values are getting closer and closer to 4. So as my x values move closer to 2 from both sides, from the left and the right, I can see that my y values are approaching 4. Similarly, if we wanted to look at a different limit, we could pick a different x value to approach. So if we want to consider the limit as x approaches 3 of f of x, I'm now asking what y value am I going to be approaching as x gets closer to 3. So again, I'm going to pick values close to 3, and I'm going to use those to see what y values I'm approaching. So I start somewhat close to 3, but then I move closer and closer on either side to where that 3 is. I'm moving up from the left and down from the right, and I can see that the y value I'm approaching is going to be approximately 9. So as I consider limits, I want you to take careful note that I'm getting close to the x value that I want, and I'm getting close from both sides. Now, you may be thinking, why can't I just go to 3 and find the y value? Well, this is a continuous function, so that would work out okay for us here. But with limits, we never actually plug in the value because it's really powerful to be able to find a y value if one doesn't exist. Imagine there was a hole there. We would still be able to find the limit because we never actually plug in the value. Instead, we approach it, and therefore we are approaching the y value. Let's look at a picture where this will be represented. Consider the function given here. F of x equals x squared minus x minus 2, all divided by x minus 2. If we wanted to consider the limit as x approaches 2 of our function here, we notice that at 2, we have this little discontinuity. We have this hole because this function doesn't exist at 2. If we tried to plug in 2 into our function, we would see that we'd have 0 in the denominator, and we never, ever, ever want to divide by 0. So we have to be careful about what we do with this function. However, limits are powerful in that we can get really, really close to 2 without actually plugging in 2. So we want to consider what happens as we get close to 2 from either side. And when we do that, this y value is going to be approaching 3. So here, even though we can't plug in 2 into our function, we can find the limit of what we're getting close to in terms of y as we get close to 2. So even though we can't plug it in, we have some information about how this function behaves. So this becomes really powerful when we have things like discontinuities or places where we would be otherwise not able to plug numbers in. Now, this idea that I'm looking at functions from both sides, the left and the right, is really important. So now let's consider the important things we've talked about so far. Let's summarize them, and then let's do some examples. So the important points so far are that limits are important because they allow us to look at how functions behave even if they don't exist. So we said we could still take the limit even though the function didn't exist at that point. We could still see what we were approaching at that point. We also said that we need to look at the limit from the left and the right when we looked at our graphs. So there's some notation that goes along with this important point. In order for a limit to exist, the limit from the left has to be the same as the limit from the right. And when we do these particular calculations, which we'll see how we do these algebraically, they have slightly different notation than our regular limit. So when we take a limit from the right, notice this little plus symbol next to a. That means when we're approaching a number, we're approaching it from the right. That plus indicates that we're a little bit bigger than the independent value. Now, when we approach a number from the left, we're going to use this little minus symbol to indicate that we're approaching it from a little bit less than the number we're approaching. So for example, in the last one we looked at, we were approaching 2. So that means when we were approaching from the left, we were considering things like 1.9. And when we were approaching from the right, we would consider something like 2.01. So something a little bit bigger and a little bit smaller is what we're talking about when we're talking about these limits from the left and the right. So here, we want to look at what's going to happen if these are different from the left and the right. An example of that would be a piecewise function. So consider the function that I'm drawing below. Consider that our point here that we're concerned about is what's happening at 2. The limit from the left is going to be the y value of this closed point, whereas the limit from the right is going to be the value from the open interval. So these are going to be different because the y values that they're approaching are different. And if the limit from the left is different than the limit from the right, then the limit itself does not exist. Now, you can have a limit from the left exist and a limit from the right exist, but the limit itself, the limit without a plus or a minus, would not exist if those are different. However, if they're the same, then our limit does exist. So we're going to look at some examples of this, how we compute this both algebraically and on graphs, and we're going to start to determine how these limits work. Example 1. Find the limit as x goes to 3 of 9 plus x. So again, the idea that we have to go from the left and the right means we need to be getting closer and closer to 3 from both the left and the right. So in the first column, I've picked numbers that are getting closer to 3 from the left. So I'm going to pick numbers slightly smaller than 3, but that are approaching 3. So 2.9, 2.99, 2.999. So here, we're going to start by plugging in the 2.9 into the given function, and we're going to get 11.9. Now we plug in 2.99, and we get 11.99. And when we plug in 2.999, we get 11.999. So here, the limit from the left, I think we can safely say, is approaching 12. So the way we would write this is the limit as x approaches 3 from the left, because those numbers are a little bit smaller than 3, of 9 plus x equals 12. I know that I'm approaching 12 because every time I get a little bit closer to 3, I get a little bit closer to 12, because every time I add another 9, I'm getting closer and closer to 12. I also, however, have to check what's happening as x approaches 3 from the right, so something a little bit bigger. So I'm going to do 3.1, 3.01, 3.001. By adding in more zeros, I'm getting closer and closer to 3. So when I plug these numbers in, I'm going to get 12.1, 12.01, 12.001. And again, I can see that these numbers are approaching 12, because every time I get closer to 3, there's another 0 before the 1, which means I'm getting closer and closer to 12. So this limit I can write as the limit as x goes to 3 from the right, so with that plus sign, of 9 plus x equals 12. So both the limit from the left and the limit from the right exist. Now, because these two limits are equal, because they are the same, that means that the limit as x approaches 3 of 9 plus x is going to equal 12. Because these are equal, this limit exists, and it's the value of 12. Now let's look at another example where the function is a little bit more complicated, and the answer may not be as obvious as the last one. So here, we want to find the limit as x approaches 0 of the natural log of 2 plus x minus the natural log of 2, all divided by x. Notice that if you tried to plug 0 in, which we don't want to do because with limits we approach and we never plug in, you're going to end up with a 0 in the denominator. So that means we can't even just plug in to try to figure out what the limit's going to be. So instead, we have to take the same approach as before, where we're going to get really close to 0 from both the left and the right to see what it's approaching. So first here, we're going to take the limit as we approach 0 from the right. From the right-hand side, I'm going to use the values 0.1, 0.01, and 0.001. We always want to get as close as we can, so we don't want to pick integer values because those are actually kind of far away. So things like the tenths place, the hundredths place, the thousandths place are much, much closer to 0. So as we approach from the right, I'm going to take each of these x values and I'm going to plug it into my function to see what the corresponding y values are and hopefully be able to use those patterns to determine what we're approaching. When I plug in 0.1, I get 0.4879. Now here, my calculator only gave me 4 values, so I wrote them all down. You'll have to make a decision when you're doing these types of limits on how to round. If a problem specifies how you should round, that's how you should stick through it on your limit. Otherwise, 4 decimals is usually safe. When I plug in 0.01, I get 0.4988 to 4 decimal places. When I plug in 0.001, which is the closest value I have to 0, I get 0.4999 when I round to 4 decimal places. So I'm feeling fairly confident that the limit as x approaches 0 from the right is approaching 0.5. Those numbers appear to be getting closer and closer to 0.5, and I could try a couple more zeros out just to see, but I'm feeling pretty confident about that. Let's also check what happens as we approach 0 from the left. So when we approach 0 from the left, that means we are on the negative side of the number line. So the numbers I pick are going to be negative 0.1, negative 0.01, and negative 0.001. So again, I'm going to plug these numbers into my function to see what the y values are approaching. When I plug in negative 0.1, I get 0.5129. When I plug in negative 0.01, I get 0.51 0.5013. And when I plug in negative 0.001, I get 0.5001. So again, looking at these values, I see that the decimals and zeros are going out further and further, and I feel fairly confident that this limit is also approaching 0.5. So since my limit from the left is the same as my limit from the right, that means that the limit itself exists and that limit is 0.5. Again, I can have the limit from the left exist and the limit from the right exist, but the limit itself would not exist if those had been different values. We'll look at some examples of that later. Let's take a look at a graph and see if we can do some limits using what we've learned about left and right limits and figuring out when limits exist. So consider the graph of f of x below. This is called a piecewise function because this is defined by different functions for different parts of the graph. We can see that there's some holes and some jumps, so we're going to have to be really careful with our limits. There's three limits that we want to compute here. The first one is the limit as x goes to 1 of f of x. So as we approach 1, we're considering what happens to these functions. So we're going to start by seeing what happens as we approach 1 from the right. So something to the right of 1, that means we're defined by this function up here, this line. So as we approach 1 from the right, the y value that we're approaching is 3. So again, since we never actually plug in 1, we're asking what happens when we get close to 1 from the right. As we get close to 1 from the right, we get close to 3. Now, when we consider what happens as we approach 1 from the left, we're on this sort of U-shaped function. So here as we approach 1 from the left, we're approaching a y value of 1. So here the limit from the right exists, the limit from the left exists, but they're different, which means that the limit itself, the limit as x goes to 1 of f of x, does not exist because it's different when you approach it from the left and the right. Now let's consider what happens as we approach negative 1. So as we approach negative 1, again, we're going to consider what happens from the right and the left. So let's start by looking at what happens when we approach from the right. So that means we're starting with values a little bit to the right of negative 1. So as we approach negative 1 from the right, the y value that we're approaching is positive 1. Similarly, when we approach negative 1 from the left, we are also approaching a y value of 1. So here, the limits from the left and the right both exist, and they're the same. If they're the same, that means the limit itself exists, and the limit equals 1, because that's what the limit from the left and the right both equaled. So here, at negative 1, our limit exists. Now, finally, let's look at the limit as x approaches 2. So again, we're going to consider what happens from the left and the right. So the limit as x approaches 2 from the right of f of x means that we're on this upward sloping line here, and we're considering what happens as we get close to 2 as we're coming down from the right. So we can see that the y value as we approach 2 from the right is going to be 2. If we look at the limit as x approaches 2 from the left, however, now we're on this horizontal line. So as we approach from the left, the y value that we are approaching is 3. So again, the limit from the right exists and the limit from the left exists, but since they're not the same, that means the limit itself as x goes to 2 does not exist. So when you're considering whether or not limits exist, you need to be looking at what's happening from the left and the right to figure out if the limit itself exists. While we can always use charts to plug in and get close to numbers with algebraic formulas to see what the limit is, sometimes it's useful to try to simplify what we're looking at the limit of before we take the limit. So for example, consider the limit as h goes to 0 of 2 plus h squared minus 4 all divided by h. So this is another case where if we had tried to plug in h equals 0, we'd end up with a 0 in the denominator and numerator, and that wouldn't be so good for us. So we know that we want to make a chart, and we want to see what happens as h gets close to 0 from the left or the right. But what we can do here is we want to first see if we can use algebra to simplify the expression. So the limit part stays the same. We're still taking the limit as h goes to 0, but now in the top, I'm going to square out the 2 plus h squared term. When I square that out, I'm going to get 4 plus 4h plus h squared. And then I have a minus 4. And that's still all divided by h. Now, combining like terms, I can look at these constants. So notice I have a 4 in the first term and a minus 4 at the end. So I can cancel those out, and I'm left with a 4h plus h squared over h. And what I can do here is I can factor out an h, so the limit as h goes to 0. So on the top, if I factor out an h, I'm left with a 4 plus h divided by h. And the reason why I wanted to factor out that h is so I could cancel it with the h on the bottom. So now I have the limit as h goes to 0 of 4 plus h. So this is a simpler function to work with, and I have a pretty good intuitive idea of what this limit is going to be. So again, I need to consider what happens as I pick my h values close to 0. So again, from the right, I will pick 0.1, 0.01, and 0.001. And then my function, 4 plus h, that's going to give me 4.1, 4.01, 4.001. And I feel comfortable saying that that's approaching 4. When I consider what happens as I approach 0 from the left, so again, I'm on the negative side of 0 on that number line. I'll have negative 0.1, negative 0.01, negative 0.001. When I plug that into 4 plus h, I'm going to get 3.9, 3.99, 3.999. So now I have the limit as h approaches 0 from the right is 4. And I have the limit as h approaches 0 from the left is 4. So therefore, the limit of the whole thing is going to equal 4. I want to point out that here we use the variable h instead of x. It doesn't matter what your variable is because you always assume that whatever the variable is under the limit is your independent variable, and you plug everything in the same way. So again, the point of this example is that sometimes it's easier to simplify your function first before you take limits to do your calculations, and we'll see why that might become powerful in the next section. So finally, we want to have a good intuition about looking at a graph and determining where the limit is not going to exist. So you can see that at the points where the function is continuous, the limit is going to exist because we're always going to be approaching the same y value from the left and the right. The points where we get concerned are the points where our function is jumping or has what's called discontinuities. We're going to talk more in depth about this in the next section. But here, where our graph doesn't seem to continue in a nice even flow are the points where we're really concerned about the limits. So here, my limit's not going to exist when x equals -1, because again, the limit from the left is going to be 0, and the limit from the right is going to be 1. So those are different. And then it's also not going to exist at x equals +1. So at +1, the limit from the left is going to be 1, and the limit from the right is going to be 2. 2, and those limits are different, so the limit does not exist. And there's even another awkward point here because the actual value at 1 is -2, and neither of those limits even come close to the actual value. So when we have piecewise functions, we're always concerned at the points where our function takes on a new part of the graph. So when you look at these types of pictures, you can identify where this limit's not going to exist by finding these discontinuities.